5-4, exponential and logarithmic equations now. So we're going to solve these equations, hopefully some more complicated ones of exponential and logarithmic, and use exponents, exponential and logarithmic equations to model some real world problems. So here's an example of a problem. We're going to have an original equation like 2x equals 32. We can rewrite that. We'll change the right side. Instead of 32, we'll make it 2 to the 5th. And then we'll use the one-to-one property to say, okay, well, if 2 equals, we know the base is equal, so therefore the exponents have to be equal, and x has to be 5. So by getting it to rearrange to look the same as far as the bases, we know the exponents are the same, and we can get a solution that way. So you can do this with several other examples. You can look through this, but we're going to do some examples, you know, from the homework and in this section that will hopefully help. But you know, here's an example of then another type of problem we can do where we can take the natural log of both sides of an equation, and when we do that, the natural log of e it cancels. It goes away, and I'll show you why that is later, but basically we can just bring the exponent down then, and we'll end up with x equals the natural log of 7. Okay? We can actually do the same thing here, where we can do e to both sides, where we raise this to the exponent of e to both sides, and then what happens is the e natural log cancels, and we end up with x equals e to the negative third. So we'll do some examples of these. Some strategies. We're going to rewrite the original equation in a form that allows us to use one-to-one properties. We'll rewrite exponential equations in log form and apply the inverse. And we'll rewrite logs equations in exponential form and apply the inverse. So here's a couple of examples. You're going to solve problems like this where this is pretty straightforward with the one-to-one property. You can see we have the same base, so we must have the same exponent in order for this equation to be true. So what we can do is take the exponent here, negative x squared, instead of equal to negative 3x minus 4, right? Exponent has to equal exponent. Now what I have is a quadratic, and I know how to solve quadratics. I'm going to add the x squared to both sides, so I have 0 equals x squared minus 3x minus 4. And I believe this factor, so that'll save us a little time with the quadratic formula. X minus 4, x plus 1. And so the solutions, x equals 4, and x equals negative 1. We should check those in the original equation, make sure that they both work. They should. But there's two solutions then to this problem. Okay. Now, we're also going to do a one like B, where we have 3 times 2 to the x power equals 42. Obviously, we want to divide both sides by 3 first, and that gives us 2x equals 42 divided by 3. 14. Okay, now we're going to try to rewrite 14 as an expression of 2 to the exponent. So let's do 2 to the x equals, we'll make it 7. Actually, I'm not able to use the one-to-one property here because I can't rewrite 7 as 2 to something. So what I'm going to have to do is take the log of both sides. So from this step here, let's take the natural log of both sides. I use natural log because it's easier to write, only 2 letters instead of 3, but you can use any log you want as long as you use the same base on both sides. Now I can bring down the x, and that gives me x natural log of 2 equals natural log of 14. Divide both sides by the natural log of 2. And you get your answer, which is natural log of 14 over natural log of 2. And that gives you 3.8 if you do that in your calculator, approximately, rounded to the nearest tenth. Okay, it says round 3 decimal places if necessary, so I guess that would be 3.807. Okay. So basically, to solve a logarithmic equation, you can, here's one where you can write it in exponential form, or take the e of both sides. So I like to, when I'm doing these problems, write in exponential form. So that's where you take base to the exponent equals the argument. So I write it as e to the third equals x. That allows you to do it your calculator to find x, which is what they get eventually if you take e of both sides. So the other way to do it then is to raise both sides, like put e as a base of both sides. So what's there becomes an exponent. And the e of natural log cancels, you get x equals e to the third. Either way works. do a couple example problems. Let's solve natural log of x equals 2. I like to put it in exponential form, so I like to say the base is e to the exponent 2 equals x. Okay, if you like to raise both sides to the e, that's fine. In which case this would cancel and you get x equals e squared. Either way, you get e squared for your answer. If you were to do that to, round to the nearest tenth. You'd get about 7.4-ish. Okay, so you definitely have to solve problems like that. Let's try a little bit more difficult one here. Let's solve this problem. Now, for this one, I have log base 3 of this equals log base 3 of something different. Now, I would probably try to use the comparison property here to say that, okay, well, since the log base 3 is the same on both sides, then 5x minus 1 has to equal x plus 7. And then solve for x. So subtract x from both sides, and you get 4x. Add 1 to both sides, you get equals 8. So x must be 2. Okay? All right, so let's try another one. This is log base 6 of something minus log base 6 of something else equals log base 6 of some third quantity. So let's try to simplify this. I would change this. We had a property that said log base anything, so we'll say log base 6 of two things being multiplied, u times v, for example. Actually, I'm sorry, let's do two things divided, is equal to the log that base of the first thing minus log that base of the second thing. It's one of the properties we had. So you can see we could go backwards from this right here being the right side, and we could change it into this, a division. So we're going backwards with this property. All right, so let's make that log base 6 of the 3x plus 14 divided by 5. And that equals the log base 6 of 2x. And now I can use the one-to-one property again to say that this equals this. So I know that 3x plus 14 over 5 has to be equal to 2x. And now I'd multiply both sides by 5 to make this 10x. And then I'd subtract 14 from both sides. That's fine. And subtract 10x from both sides, and you get negative 7x equals 14. Negative 14, so x must be 2. Okay? All right, let's try an investment problem then. Let's say we've deposited $500 in an account that pays 6.75% interest. We're going to compound this continue. How long will it take to double your money? Okay, so we know that compounded continuous, the formula is A equals P times e to the RT. Okay, we've deposited $500, that's our principal. Our rate is 6.75, so we're going to write that as 0.0675. The question is how long? So we're answering this question for time, and we want our money to double, so we want this to be 1,000 for our final value. So this is the equation we're solving. We're going to divide both sides by 500, and that's going to give us 2 equals e to the 0.0675t. I'd probably take the natural log of both sides now, because when you take the natural log, you can bring the exponent down, and this cancels. Natural log of e is just 1. And if you're not sure that it is 1, what you can do is say, okay, what is the natural log of e? Well, let's call it something, call it x. And now change it into exponential form. You'll see that the base, e, to the exponent, x, is equal to e, which that's just e to the first. So right from there, x equals 1. So when you do base to the exponent equals the argument, when you change it from log form into exponential form, it's easy to see that x is 1. Okay, so if you don't know that, all you need to know is that these cancel. And you end up with natural log of 2 is equal to 0.0675t. And now divide both sides by 0.0675, 0.0675, and you end up with 10.3 approximately. How long will it take for your money to double? That's years. So I would say let's round that to 11 years. It's somewhere in the 10th year it does it. So since usually we don't talk about portions of years with decimals, let's say it's going to take 11 years for our money to double. Okay. We can look at a graph of this. Here's the equation, it's exponential growth. And about 10.3 years, the money doubles from 500 to 1,000. Okay. All right, I hope that helps. We'll make a homework help video as well.